interesting optical phenomenon, refraction. Just like every time, let us try to define refraction by performing a simple activity.
That the beam of light has changed its path when it traveled from one transparent medium to another. This transmission of light across a boundary between two media is accompanied by a change in speed. This means a change in wavelength too, as speed is equal to wavelength into frequency, which remains constant.
Light refracts at the boundary due to a change in the speed. There are two prerequisites for refraction to happen. One, light must change speed when crossing the boundary, and two, should approach the boundary obliquely.
As we discussed, light travels at different speeds in different media. The ratio of speed of light in vacuum is to speed of light in medium is the absolute refractive index of the medium, which is represented by n. N of material is equal to 3 into 10 raised to 8 meter per second divided by v, that is velocity of material. Different materials have different refractive indices. Higher the absolute refractive index, lesser is the speed of light.
Okay, the direction of refraction depends upon the refractive index of the two materials. If a ray of light passes across the boundary from a material in which it travels fast into a material in which travels slower, then the light ray will bend towards the normal line. This is known as the FST rule, fast, slow towards the normal.
If a ray of light passes across the boundary from a material in which it travels slowly into a material in which travels faster, then the light ray will bend from away from the normal line. This is known as the SFA rule. That is, S is for slow, F is for fast, and A is for away from the normal.
The angle of incidence and refraction are the angles made by the incident ray and refracted ray with the normal respectively. The study of the refraction of light as it crosses from one material into a second material yields a general relationship between the signs of the angle of incidence and the angle of refraction.
This is general relationship is expressed by the following equation: n of I into sine theta of I is equal to n of R into sine theta of R, where theta of I is equal to angle of incidence and theta of R is equal to angle of refraction. N of I is index of refraction of the incident medium and n of R is equal to index of refraction of the refractive medium.
We can also write this equation as sin theta r upon sin theta r is equal to nr upon ni is equal to c upon vr upon c upon vi, that is equal to VRI upon VR.
Good day. Today we will see an experiment depicting refractive index. We need a large beaker, a small beaker, and sunflower oil, which is in this green bottle. We place the small beaker inside the large one. We start pouring oil inside the small beaker and fill it up to its brim. We find that the beaker is still visible. Now we keep pouring oil into the beakers. And lo, it's disappeared. This happened because light passes through the glass undeviated, as the refractive indices of oil and glass are almost equal.
What are magic tricks regarding refraction?
So, as said before, light will not refract if 1. The speed of the light stays the same, or 2. The incident ray is perpendicular to the boundary.
That's all from the first part of the show. But stay tuned as our friends Raman and Edison will explain how nature of man and prisms make use of refraction to conjure up some interesting phenomena.
Now we'll take a convex lens and pass light rays through it. We find that the rays refract and come to a point. This point is called the focus, the principal focus of the convex lens. This also demonstrates the refraction of concave lens and pass light rays through it. We find that the rays diverge after passing through the lens, but they appear to meet from a common point. This point is called the principal focus of the concave lens. The light rays are very faint. This also demonstrates the refraction of light. Good morning, students. Today we are going to learn refraction through a rectangular glass slab. We see that this ray AB passes through the rectangular glass slab obliquely. So it bends, and the second time it bends, it goes back into the air. This ray AB is called the incident ray. The ray BC is called the refracted ray as it is refracted from AB. And the ray CD is called the emergent ray as it emerges out of the glass slab. And there is a normal or a perpendicular to the point of incidence drawn, OO dash and NN dash. We find that when the ray AB enters into the glass slab, it bends towards the normal, whereas when it goes back out of the glass slab, it bends away from the normal.
Excuse me, sir, I have a doubt. Why does the refracted ray bend towards the normal and the emergent ray bend away from the normal?
I have a good explanation for that. It is believed that light is made up of waves. This is called the wave theory of light. So if we draw waves as light, these waves travel through air at a constant speed, 3 into 10 raised to 8 meter per second. So now when they enter into the glass slab, the speed of light decreases. As a result, this part of the wave enters the glass slab first. So their speed decreases first, while the other, which is still in the air, has a different speed. So by the time it enters fully into the glass slab, it has already bent as a result of the decreased speed. The same is true when it goes back into the air. This part of the wave first goes out of the glass slab. So it bends a little bit while the other part does not. When the entire wave comes out of the glass slab, it appears to be bent again. So we also find that this ray AB, when extended forward, is parallel to this CD.
So it's like this. It's coming here, it's bending here, coming here, and again bending.
So it bends twice, once at B and another time at C. Thank you.
Hello and welcome to the second part of today's episode of Learn Science, hosted by Edison and Raman.
In this part, we will start with prisms. What was not mentioned earlier in this unit is that the index of refraction values are dependent upon the frequency of light. For visible light, the n value does not show a large variation with frequency, but nonetheless, it shows a variation.
For instance, for some types of glass, the n value for frequencies of violet light is 1.53 and the n value for frequencies of red light is 1.51. The absorption and re-emission processes causes the higher frequency violet light to travel slower through ground glass than the lower frequency red light.
It is this difference in n value for the varying frequencies and wavelengths that causes the dispersion of light by a triangular prism. Violet light being slowed down to a greater extent by the absorption and re-emission process refracts more than red light.
Upon entry of white light at the first boundary of a triangular prism, there will be a slight separation of the white light into the component colors of the spectrum. Upon exciting the triangular prism at the second boundary, the separation becomes even greater and Vibgyor is observed in its splendor.
This phenomenon is termed as dispersion of light. The fact that red light gets refracted the least also made use of in traffic lights for trains. They use red color to signal the train to stop, as it cannot be refracted easily in the atmosphere.
Another colorful effect of refraction is the rainbow. A rainbow is most often viewed as a circular arc in the sky. An observer on the ground observes a half circle of color with red being the color perceived on the outside or top of the bow, whereas observers in an aeroplane or a helicopter can often look both upward and downward to view the complete circular bow.
Each rainbow in the sky acts as an individual prism, letting up light into the Vibgyor colors. The red light is refracted out of a droplet at sharper angles towards the ground than blue light. Thus, when an observer sights at a sharper angle with respect to the ground, droplets of water within this line of sight are refracting the red light to the observer's eyes.
Similarly, when sighting at less steep angles, droplets of water within this line of sight are directing blue light to the observer's eye, while the red light is directed downwards at a steeper angle towards the observer's feet. This is why the red light that is observed at the top of a rainbow and the blue light can be seen on the bottom of a rainbow.
On this colorful note, we bid you goodbye. We hope that you continue to learn and enjoy science with us.
So next week, we shall meet at the same time and same channel, but with a different topic.
The bottom of the glass slab appears to be raised. The printed material on the glass slab seems to be raised. The pencil immersed in a water seems to be displaced. Why? Light seems to come from a different direction. This makes the ray displaced at the interface at the same extent. In kerosene, when it displaces, replace the glass slab with a transparent, you will find that the extent of effect is different in media that differ, they are different. When light appears traveling obliquely from one medium to another, what happens to the direction of proportion? The light in the second medium changes. This is called refraction. Refraction of light to extend through a glass slab. Take to transparent media, keep it on a rack. Drop a light from a direction of your sight. This will result in the bending of light. As it goes all along, the speed changes on and on. Take anything, a glass slab or a prism. Starts from rarer to denser towards the normal medium. Goes through denser to rarer away from the normal medium. This was easy as you saw. Now here comes the Snell's law. Sine of incident angle is proportional to the sine of refracted angle. This is called Snell's law of refraction. Learn refraction, no time to rest. Let's end it. The constant of proportionality is called the refractive index. Finally, it ends and